السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. إن شاء الله we'll continue today talking about logical agents. We start last time giving an introduction about knowledge based agent. And today inshallah we'll talk about logic and propositional logic. We also introduced the running example of Wampus World, and we talked about how we or what the process of a knowledge-based agent, and how the agent can have sentences in the knowledge base and updates these sentences based on what it perceives and what it inferred from the existing sentences. Today inshallah we'll talk about how we will represent the knowledge base. Okay, so we'll start with logic. Logics in general are the formal language that we use to represent information. Okay, and one of the logic systems that we would use is the proposition logic that inshallah towards the end of the lecture we will introduce and talk about. So it is the representation language. It is how we represent the information or the sentences in our knowledge base, and these languages we will use also to draw conclusions, to infer or derive new sentences from existing ones. We have two things in a logic language. First is the syntax, which defines the validity of sentences, or how the sentences are written in this language. For example, the arithmetic logic language, the language in which we write arithmetic, has this sentence, and it is a valid sentence in that logic. Okay, so x plus 2 is greater than or equal to y. That's a valid sentence. Okay, but let me change this. Yeah, but this one, for example, x2y plus greater than, is not a sentence, is not a valid sentence. Okay, how did we know that? We know that from what we call the syntax. Okay, the syntax. So the syntax of the language defines how the sentences are written. Okay, so this one is valid, this one is invalid. So that's the first thing about the language, the syntax. The other thing is called the semantics. Okay, the semantics define the meaning of the sentences. Okay, so this sentence by itself doesn't tell us the meaning of it. Okay, but the semantics tell us the meaning of sentences. In particular, in our case, it defines the truth of a sentence in a word. Whether the sentence is true or false is defined by the meaning of the sentence or the semantic of the sentence. For example, the same sentence, x plus 2 is greater than or equal to y, is true if and only if the number on the left side, x plus 2, is not less than the number on the right side, which is y. That's the meaning of this sentence, right? So that's the semantics. Okay, so the semantics define the meaning. Now, this sentence and also define the truth. The meaning here in our context means the truth of the sentence, which means that the semantic of this of the sentence will define when this sentence can be true and when it can be false, because there are cases where this sentence will be true and this sentence will be false, and that's defined by the semantics, the meaning of the sentence. Okay, so this sentence will be true in a world where x is 7 and y is 1, because now the left hand side will be 9, the right hand side is 1, so it's true. How did we know that? From the semantics, from the meaning behind the sentences. It can also be false in a world where x is 0 and y is 6. Okay, so the meaning or the semantics of the sentence defines the truth of that sentence in a specific world. Okay, any question about this, about syntax and semantics? I think the difference is clear. Any questions? Okay, now let's move on to a very important concept in this session, not only in today's lecture, but in the session of logical agents, which is called entailment. Okay, entailment. Entailment means that one thing follows logically from another. We write it that way. Alpha entails beta, okay, which means that beta is followed logically from alpha, okay, or we infer beta from alpha, or alpha implies beta. I think that reminds you with something that you studied in an earlier course. Okay, or we can say if alpha then beta. All of these things are the same thing, and all of them are called or under the umbrella of entailment. Okay, entailment. So alpha entails beta. That means that whenever alpha, so that's actually the definition now, in every world that in which alpha is true, beta also is true. So that's the formal definition of entailment. So sentence alpha entails sentence beta if and only if, whenever, or if in every world, whenever alpha is true, beta also is true. Okay, that's exactly the implication statement that we learned about in propositional logic in a discrete math course. Okay, when we say alpha implies beta, that means that whenever alpha is true, beta is also true. Okay, here we call it, in that context, we call it entailment. Entailment. Okay, if alpha is true, then beta is also true. Okay, so that also applies generally to a knowledge base. So we can have alpha to be a knowledge base, multiple sentences, not just one sentence, and we can say that the knowledge base entails a sentence beta if and only if beta is true in all worlds where alpha is true. So that's a bit different from, different in words, but not different in meaning from the previous definition. Okay, so here we said that whenever alpha is true, beta is true. Okay, we can say it in a different way. In all worlds where alpha is true, okay, beta is also true. In all worlds where alpha is true, beta is also true. What do we mean by all worlds here? All worlds here means all possible scenarios. Okay, all possible situations. Okay, in all possible situations where alpha is true, and if that's the case, that in all possible worlds, in all possible situations where alpha is true, beta is also true, that means that we can entail beta from alpha, or alpha entails beta, or alpha follows logically from, beta follows logically from alpha. Okay, let's see examples. X equals 0 entails xy equals 0. Why is that? Because whenever x is 0, which means whenever x is 0 is true, if x is 0, then of course xy equals 0 is also true, regardless of the value of y. Okay, so xy is 0, xy is equal to 0 is always true whenever x is 0. Okay, so we can say that x is 0, x equals 0 entails xy equals 0. Okay, so in all situations where x is 0, xy is also 0. Another example, if the knowledge base has two sentences like that, Al-Rayyan won, let's say that there is a football game and Al-Rayyan won in that game. There's another game in which Al-Sad won, and we have these two sentences in the knowledge base. Al-Rayyan won and Al-Sad won. Now this knowledge base entails another sentence, which is either Al-Rayyan won or Al-Sad won type. Why is that true? Because whenever the knowledge base is true, which means that this is true and this is true, of course the third sentence is true. In fact, the third sentence is true whenever at least one of these is true. Okay, but that also means that here the knowledge base, whenever these are both true, then this one is also true. Okay, so we can say that we can entail this sentence which is either Arrayan 1 or Alsad 1, from the knowledge base. Okay, in fact, we can also entail that both Arrayan and Alsad 1 from these two sentences. Although it's trivial, of course, this example is maybe more trivial than the previous one, but it's still true. Okay, it shows that whenever the knowledge base is true, then we can entail from it the last sentence or the third sentence. Okay. So entailment is a relationship between sentences. Sentences by themselves in an abstract way, they are syntax. Okay, but the entailment is a relationship between the semantics, because we say that if alpha is true, and we cannot tell whether alpha is true or not without the semantics of the language or the sentence. Okay, so if alpha is true, then beta is true. If whenever alpha is true, beta is true, then we can say that alpha entails beta. Okay, and that's equivalent to saying that alpha implies beta in propositional logic, as we will see inshallah later. Any question about this? This is a very important concept, and that's a core concept behind logical agents and behind inference from knowledge bases. Any questions? Okay, so let's move on. Now we'll talk about models. You heard from me the word world before, right? Today. Okay, so the world is just a scenario, a configuration, okay, of a specific problem or environment. Models are an abstract concept of a world, okay, an abstract form of the world, okay, where we can actually see the truth, we can evaluate the truth of the sentences. Okay, so the word model and the world are related. The world is the real scenario. Most of the cases we mean by the world the real scenario, and by the model is just an abstraction of that world. Okay, where the sentences now we can evaluate. We can give a truth value for each sentence. Okay, so a model has a truth value for every sentence or every variable. Okay. It's just an abstraction of the actual world. Now we say that M is a model of a sentence. So far we said a model in general. Okay, so the model is an abstraction in general where there are there are values for every sentence or variable. When we say that we can say that M is a model of a sentence if sentence alpha, if alpha is true in M. Okay, yani in a world where alpha is true, we call that a model of alpha. Okay, so if that sentence is true in a specific model, we call that model a model of alpha. Okay, for example, the sentence xy is 0. Okay, is true if y is 0. So in a model where y is 0, alpha is true, right? So I can say that this model is a model of alpha. Okay, so that's just an example. Here is the models in a graphical way. Okay, the set of all models of alpha, we call it M capital of alpha. Okay, so every forget about what's inside now. Every x here, okay, is a specific model where alpha is true. Okay, specific configuration where alpha is true. Okay, now all of these models are called M of alpha, is a set of all models of alpha. Remember, a model of a sentence is a model in which the sentence is true. There are models in which the sentence is false. And for example, xy equals 0. Okay, that's a sentence. Okay, in a model where x is 1 and y is 2, this sentence is false. So we cannot say that this model is a model of that sentence. Okay, but any model in which x is 0 or y is 0 is a model of that sentence. Okay. Now the set of all models of that sentence is called M capital of alpha. Okay, and here we are represented by these x's. So every x here is a model of the sentence alpha, which means that for every x here, alpha is 2. Now let's assume that we have a knowledge base. Okay, and this knowledge base, these are the gray area, are the models that satisfy the knowledge base. The models in which the knowledge base is true. That means that this is the set of all models of the knowledge base, M capital of the knowledge base. Okay? So that can happen that it is inside or a subset of the models of alpha. Okay? So some of these models, some of the models of alpha satisfy the knowledge base and some are not. Okay? So M of the knowledge base is a subset of M of alpha. If that's the case, then we say that the knowledge base entails alpha. So the knowledge base entails alpha if and only if the models of the knowledge base is a subset of the models of alpha. Okay, that's another way of looking at the definition we mentioned in the previous slide. In the previous slide, we said that knowledge base entails alpha means that whenever the knowledge base is true, alpha is true, right? Let's look at this figure here. Is it the case that whenever the knowledge base is true, alpha is also true? Yes, of course, because all the models in which the knowledge base is true are also models of alpha, right? That's from that figure, all x's in the gray area are also x's in the white area. Okay, so whenever the knowledge base is true, alpha is also true. That means that the knowledge, if the models of the knowledge base is a subset of the models of alpha, then the knowledge base entails alpha. Okay, the knowledge base entails alpha. So the knowledge base entails alpha if and only if the models of the knowledge base is a subset of alpha. So whenever we see the knowledge base, we can infer alpha from that. That's the meaning behind the entailment. We can infer alpha from the knowledge base. Let's look at an example. Let's say that the knowledge base has only one sentence, just for simplicity, which is x is 0. Okay, and alpha is xy equals 0. Let's say that x takes the values 0, 1, 2, just for example, and y also takes the values 0, 1, 2. Now, what is the models of the knowledge base? What are the models of the knowledge base? These are the models in which the knowledge base is true. Okay, so it has one of the models is 0, 0, where the first one is x and the second one is y. Okay, so 0, 0 is a model for the knowledge base, right? Also, 0, 1 is a model for the knowledge base. 0, 2 is a model for the knowledge base. All of these models has the sentence x equals 0, right? Or has the value x equals 0. So all of these models, okay, are the models of the knowledge base. Now, what is the models of alpha? This is all the models where x, y is 0, the models that satisfy this. Okay, so what are these? This is 0, 0, 0, 1, 0, 2, 1, 0, and 1, 2. Right? Because anything here, it's either x is 0 or y is 0. This is, yeah, there's something wrong here. This should be 2, 0. Yeah, thank you. Yes. Okay, now looking at these two, we can see that clearly that M of the knowledge base is a subset of M of alpha. right? The models where the knowledge base is true is a subset of the models where alpha is true. So that means that the knowledge base entails alpha. Or, in other words, we can entail alpha from the knowledge base. Okay? And that's of course clear from the semantics of these two sentences, but that's how we can see it formally. Okay? Or using this definition. Any question about that? Is that clear? Is that not clear? Okay, good. So let's move on. Now let's talk about entailment in the WOMPAS world. Okay, let's take an example. Of course, I hope that you remember from last time what a WOMPAS world means. Here we have a situation where we already detected nothing in room 11. So let's number the rooms here to make it easier for us. So we detected nothing in 1-1. We moved right, and we detected breeze in 2-1. Okay. Now, just consider for simplicity the possible models, assuming only pits. Okay, so we'll just assume that there is no WOMPAS, and we don't care about the WOMPAS for now, and we care only about the pits. Okay, and let's assume that we have 3 Boolean choices. We are only concerned about having pit here or here or here. Okay, so we have actually 3 Boolean choices here: true, false here, true, false here, true, false here. So that means that we have 8 possible models in general. Okay, in the WOMPAS world, we have now 8 possible models that represent the values in these 3 cells, the values of whether we have a pit or not in these 3 cells. Okay, so we have as WOMPAS models, we have these 3 worlds. Okay, we can have a pit here and nothing here. We can have a pit here and nothing here, and so on. Okay. Faisal, do you have a question? Yes. Yeah, that's why we have 8. Yes. Okay. So we have 3 Boolean choices. So we have, of course, 2 to the power 3 possible models. Yes. Thank you. Okay. Now these are the WOMPAS models. Okay. Now let's think about the knowledge base. Okay. So the knowledge base. What are the models of the knowledge base? Let's think together here. So the knowledge base, we got we know that this is safe, and we got a breach here. Okay, so in order to get the models of the knowledge base, we need to find out from the possible WOMPAS models, the possible world models here, which of these satisfy the knowledge base, which of these don't contradict with the knowledge base. These will be the models of the knowledge base, or the models in which the knowledge base is true. Okay, so the fact that we didn't sense anything here, that means that there is no pit here, right? Okay, but there might be a pit because we sensed breach here. We might have a pit here, and we might have a pit here. Okay, so that model is a model of the knowledge base. This model is not, because it doesn't satisfy what we know from the knowledge base. Okay, we know that there is no breach here, which means that we cannot have a pit here. So that's not a model of the knowledge base. This one is a model of the knowledge base because we don't have anything here, and we might have a pit here, right? So that it doesn't contradict with what we know in the knowledge base. So this model satisfies the knowledge base. How about this one? Can this be a model of the knowledge base? No, it can't, because we had a breach here, right? So breach here means that um, means that we might have a pit here or here, right? We cannot have nothing in both. So this one is not a model of the knowledge base. How about this one? Again, this is not, because we have a pit here. We cannot have a pit here. This one, we have pit, we might have a pit here or a pit here. That's okay. That satisfies what we have in the knowledge base, right? It doesn't contradict anything in the knowledge base. So that's a model of the knowledge base. This one is not, because we don't have a pit here. And this one is not also, because we don't have a pit here. So the models of the knowledge base is this one. So we can say that this is M of the knowledge base. Okay? Any question about this one? Okay. Now let's say that alpha 1 means that room 1, 2 is safe. So that's a sentence. Okay, room 1, 2 is safe. Okay, first, where are the models of alpha 1? Where are the models of alpha 1? Faisal? Yes, so room 1, 2 is this one. Okay, so safe means we don't have any pit. So this one is, so let me change the, okay, so this one is a model of alpha 1. So that's alpha 1 now. Okay, so this one is a model of alpha 1. How about this one, Faisal? This also, and you said also this one, because all of these three. Anything else? Yes, this one. Yes, this one is also a model of alpha 1, because it satisfies the sentence alpha 1. All of the others are not, because 1, 2, actually this one also is, this one also satisfies, right? Oh no, this one has a pit here, pit here, pit here, pit here. So all of these are not models of alpha 1. So where are the models of alpha 1? This is, oh sorry, so these are the, okay, so this one is M of alpha 1. Okay, now can we say anything about alpha 1? Can we entail alpha 1 from the knowledge base? Anyone? And based on M of the knowledge base and M of alpha 1, can we entail anything about alpha 1? Or can we say that the knowledge base entails alpha 1? Okay, Faisal again. Yes, so whenever the knowledge base is true, alpha 1 is true. Or we can say that because M of alpha 1, M of the knowledge base is a subset of M of alpha 1, that means that the knowledge base entails alpha 1. Okay? Any question about that? Type. What if we have now alpha 2, which is room 2, 2 is safe. First, where is M of alpha 2? This one, okay, this one is M of alpha 2, right? Because this is room 2, 2, room 2, 2 is safe here. Again, it's safe here, so this is included. This one is not. This one is included, right? This one is included. This one is not. This one is not. And this one is not, and this one is not, right? So let me remove just to be easier. Okay, so we remove everything about alpha 1 now. Okay, so where is m of alpha 2? M of alpha 2 now has these four models. Okay, so this is m of alpha 2. Oops, sorry, m of alpha 2. Okay, now can we say anything about alpha 2? Can we say that the knowledge base entails alpha 2? Anyone? Do you think that we can say that the knowledge base entails alpha 2 now? Of course not, as Saad said, because it's not a subset. Okay, m of alpha 2 is not a subset of the knowledge base. Sorry, m of the knowledge base is not a subset of alpha 2, so we cannot say, so notice this, okay, so the knowledge base doesn't entail alpha 2. The knowledge base doesn't entail alpha 2. Okay, is that clear now? So the knowledge base entailed alpha 1, as we saw earlier, but it doesn't entail alpha 2. Any question about this? Type. Let me ask you a question here. If that's the case, can we say that alpha 2 is false if the knowledge base is 2? And here, when we said that the knowledge base okay, it goes like that. We said that the knowledge base entails alpha 1. What does that mean? It means that if the knowledge base is 2, then alpha 1 is 2. Okay? Type. Now, the knowledge base doesn't entail alpha 2. Does that mean anything about alpha 2? Yani if the knowledge base is 2, alpha 2 is false, مثلا? What do you think? Anyone? Anyone other than Faisal? I hope. Saad, can you pick up the mic, please? Type. Anyone? Edwan? So we can say that alpha 2 is false. But look, yes, this sentence is correct. Yes, but can we say that alpha 2 is false? Or alpha 2 is 2? Can we say anything of these two? If the knowledge base is 2? Yeah, in some cases, in some models of the knowledge base, alpha 2 is 2, right? And in some models, alpha 2 is false. So this, when we fail to entail, that doesn't mean anything about this sentence. We cannot know whether this sentence is false or true unless we have something else that can tell us. Okay, but just by this, if we fail to entail a sentence, it doesn't mean that this sentence is false, and also, of course, it doesn't mean that this sentence is true. We just don't know. Okay, that's very important to understand. Okay, in this case means alpha, the knowledge base entails alpha 1. Okay, so that means that if the knowledge base is 2, then alpha 1 is 2. But here we say that the knowledge base doesn't entail alpha 2. It doesn't mean anything about alpha 2. It means we don't know the truth of alpha 2 so far. So we cannot make any judgment about alpha 2. Okay, that's very important to differentiate between entailment and not entailment. Okay, entailment means if then. Okay, so if the first one, then the second one. Okay, but if that's not the case, then we don't know about the conclusion. We cannot tell whether the conclusion is true or false. Any question about this? Yes, Ridwan. Do you have a question, or someone else, or Faisal? You have a question. Okay. Yes. Yes, alpha 1 doesn't entail knowledge base. Yes. Yeah, we don't. Yeah, we didn't get any new thing. We didn't infer anything. But now, when we say the knowledge base entails alpha 1, actually, in reality, what we do is to add alpha 1 to the knowledge base, because now it's true, right? So we can add it. So that's inference. We can now add a new fact to the knowledge base. Okay, because we know something new now, that alpha 1 is true. Okay, did I answer your question with one? Okay, any other questions? Okay, so this is the relation between knowledge base and alpha 1, and that's the relation between the knowledge base and alpha 2. Okay, now let's talk about inference. Okay, formally, or more formally. Inference is the process of deriving new sentences from old or existing sentences. Okay, and notice the word deriving here. So we get new, or we derive new sentences from old ones. That's what we mean by inference. To do that, we use an inference algorithm. Okay, inference algorithm. So we use an inference algorithm, and we will see, inshallah, examples of that in this session. Not today, but in the session. I think in the coming 2 weeks, we'll see examples of inference algorithms. If the inference algorithm can derive a sentence alpha from the knowledge base, we write it that way. Okay, knowledge base, and we write it that simple. Notice that this is 1 bar, not 2. We write I here, which is the name of the algorithm. We write alpha now, alpha here. So we pronounce it that way. Alpha is derived from the knowledge base by I. Okay, so that's not entailment. There is a difference between deriving a sentence and entailing a sentence. Okay, and we will talk about that in more detail later. Okay, but they are not the same. This terminology, okay, is pronounced that way. Alpha is derived from the knowledge base by I, or I derives alpha from the knowledge base. Okay, alpha is derived by the knowledge base, is derived from the knowledge base by I, or I derives alpha from the knowledge base. Okay, that's different from entailment. For entailment we use this symbol. Okay, for deriving we use this symbol, and we write I here, which is the name of the inference algorithm we used to derive that sentence. Okay, so this means alpha entails beta. This means beta is derived from alpha using I. Okay, or I derives beta from alpha. Now, an inference algorithm, okay, can derive things that might not be entailment. And it might be the case that it derives things or sentences that are entailment sentences. Okay, so based on that, we define 2 properties for an inference algorithm. One is called soundness, and the other is called completeness. So an inference algorithm, I, is sound if whenever it derives a sentence alpha from the knowledge base, it is also true that alpha is entailed by the knowledge base. So whatever is derived by the algorithm is actually entailment. If that's the case, then the algorithm is sound. Okay, so whatever is derived is entailment. If that's the case, then the algorithm is sound. Okay, so that's the first property. The second property is completeness. Whenever there is entailment, it is derived by the algorithm. So here, whenever something is derived from the algorithm, it is entailment. If that's the case, then the algorithm is sound. If it's in the opposite direction, then the algorithm is complete. If whenever we have something that can be entailed, it is also derived by the algorithm, then the algorithm is complete. The algorithm can derive every entailment. Okay, that's the case where the algorithm will be complete. But if whatever it derives was entailment, maybe not all entailments, but whatever it is derived from the algorithm is entailment, then the algorithm is sound. Okay, so I hope that the difference between soundness and completeness here is clear. You have to understand that there is a difference between deriving a sentence or inferring a sentence from the knowledge base and entailment of the sentence. Okay, entailment of the sentence, we defined it. Okay, but we can infer something that might not be entailment. We can derive something that is not entailment. Okay, if whenever the algorithm derives something, it is entailment, then it is sound. If anything that can be entailed from the knowledge base, okay, is derived by the algorithm, is inferred by the algorithm, then this algorithm is complete. Okay, so these are the two properties of inference algorithms. Any question about this? Yes, Mustafa? Completeness implies soundness. Let me think about it. If I am complete, then anything that is entailed can be derived, but still I can derive something that's not entailed, Mustafa, in general. Right? Okay. Okay, complete means that anything that can be entailed will be derived by the algorithm, right? That's completeness. But it doesn't say that if I derive something that it has to be entailed. Maybe there are something, maybe the algorithm derives all the entailments and also derives other things that are not entailments. Okay, so in that case, it will not be sound. Okay, thank you. Great question. Okay, if there is no more questions, then we will switch to propositional logic. And I think most of you, if not all, remember propositional logic from discrete math course. Okay, so propositional logic will be the language that we will use to represent the knowledge base. So it's a very simple logic. It illustrates the basic ideas of the logic. Okay, and here in that slide we talk about the syntax. Okay, the syntax of the propositional logic. So what is the syntax of propositional logic? We have symbols. We call them propositions or propositional variables. Okay, and these are the things that will represent the sentences in the knowledge base. We give it capital letters like P1 and P2 here. And then we write sentences and we compose sentences from existing propositions. So for example, if S is a sentence, not S is also a sentence. We call that negation. Okay, there's also conjunction. which is the AND operation. So we connect two sentences, S1 and S2, by the AND operation, and the result would be a sentence. Here we are talking about the syntax. Okay, we didn't talk yet about the semantics of the sentences. Of course, you know already the semantics of all of these operations. Okay, but in this slide we just talk about the syntax, that we can compose sentences from existing sentences. So we can do negation. Negation will give us a sentence. Conjunction will give us a sentence, which is the AND of both operations, of both sentences or propositions. Disjunction, which is the OR operation. Implication, okay, which is very similar to entailment that we discussed earlier, but it's in the word implication is used specifically or exclusively with propositional logic. And the biconditional statement, which is if and only if operation between two sentences. So these are the 5 operations by which, or connectors, by which we compose sentences from existing sentences. Now let's talk about the semantics. We said earlier that the semantics will define the truth for every sentence. Okay, so for example, one model means an assignment of a truth value, false or true, for every variable. So if we have 3 variables here, P12, P22, and P31, and we'll talk about their meaning later, but if we have these 3 variables, and we assign false to that one, and true to that one, and false to that one, this is now one model. This is one model, one world, okay, in reality, but in an abstract way, it's called a model, okay? The model has a value, true or false, for every proposition or sentence, okay? That's in propositional logic. Now, if we have these 3 variables, then we can have 8 possible models, right? We can, all combinations of true, false for all of these variables, these are possible models, okay? We have 3 variables, 2 to the power 3 is 8, and we can, of course, enumerate them automatically. Okay, you remember the truth table, when we have 3 Boolean variables, we have 8 rows. Now, each row in the truth table that you use to draw is actually a model, because we assign a value for every variable of these 3 variables. Okay. Now the rules, which actually indicate the semantics of the sentences, are as follows, and I think you are very familiar with that. Not S is true if and only if S is false. S1 and S2 is true if and only if both are true, S1 and S2. S1 or S2 is true if at least one of them is true. S1 implies S2 is true if and only if S1 is false or S2 is true. You remember from the discrete math course that S1 implies S2, that's equivalent to S2 or not S1. Okay, so that will be true if S1 is false or S2 is true, or you can say it in another way, it is false if and only if S1 is true and S2 is false. Okay, if you don't remember these things, then go back to the discrete math. That is probably you studied with me, most of you studied with me. Go back and check your notes about the implication operation. The biconditional operation, S1 if and only if S2, or it's also called equivalent to S2, is true if and only if S1 implies S2 is 2 and S2 implies S1 is 2. So it's a conditional statement, but in both directions. So this is the semantics of the proposition logic. We'll have to stop here because we run out of time. Do you have any question before we stop? Yes, Faisal. Yeah. No, but if both are true, it has to be the case that S1 implies S2 and S2 implies S1. If you are talking about the values, yes, it will be true if both S1 and S2 are true, or both and يعني it's true if the values of S1 and S2 are the same, are always the same. Okay. You're welcome. Any other questions? طيب إن شاء الله we'll stop here and talk to you on Tuesday. السلام عليكم ورحمة الله وبركاته.